All right, good morning. Microphone's weird. Good morning. Good. All right. So, exam 3 is coming up next Thursday, November 12th. Same time as last time, 6:30 to 7:30 p.m. And just like last time, where you go depends on who your TA is. And the locations are different. So don't go to the same place. You may, it depends on how they assign to you. You might be going to the same place. But in general, you're probably going to a different place. So make sure you go to the right place. If you are in Alex Porter's class, Lynn Hall is the veterinarian building. It is way south of campus. Go to Lily Hall and then keep going. Okay? If you look up a map a day or two before the exam, if you have never been to Lynn Hall, and it takes maybe 10 minutes or so to get there from this part of campus. So all right, maybe less. Depends on how fast you walk, right? But if you walk at a leisurely pace, then it takes about 10 minutes. So once again, make sure you go to the right place. And I'll talk more about the exam next week, all right? Okay, so today we're going to start chapter 11, section 10. This is a very big section. We will spend 3 days on this. Today is the first of the 3 days. We're going to talk about a special series called the Taylor, and also a closely related one called the Maclaurin series. Now remember last time, we used the geometric series to find a power series for functions that resemble this, and things that resemble the derivative and integral of that. But there's a limit to what we can do with this series here, the geometric series. Anything that doesn't look like that, or doesn't look like the derivative or the integral of that, we can't use it. For example, sine of x. We can never use this thing to get a power series for sine of x, or e to the x, for example. Now we need a way to find a power series for more general functions. For example, e to the x, sine of x, and so on. Right? So again, these guys nothing look like 1 over 1 minus x, and there's no way we can use that to get power series for these. Okay, so let's start with the definition of power series again. So we want this. Some function that we decide to get a power series for, and we want it to look like that, right? For some function that we decide to expand. And let me write out a few terms of this. Let's go up to 5, and then We'll use dot, dot, dot to take care of the rest. And this left-hand side function is the function that we decide. Again, for example, e to the x. So here I was saying that I would like to write e to the x in this form here. And we'll get into why we want to do that. But for now, I want to get the techniques down, get used to it, and then we can discuss why we want to do that and the implications of that kind of expansion. Okay, now the question here, of course, is what are the CNs? There's got to be a way we can find the coefficients of each of these that when I add all of this together, it turns out to behave just like e to the x. And one good way to do that is to use the derivatives. At some location where we want to form the power series. Okay? So we'll start with the zeroth derivative. That just means the function itself, right? At x is equal to a, the left-hand side of that power series we just wrote out, of course, is then x is equal to a, right? And what about the right-hand side? What happens when I plug a into the right-hand side here? This goes away, right? That goes away, that goes away, that goes away, that goes away. The dots go away. So what's left? C0. Good. All right, so now that's the answer to the first coefficient. We know the first coefficient has to be equal to the function value at x is equal to a. Now we take the first derivative. Okay, so looking at this one here, when we take one derivative of this, C0 is a constant. It disappears. And next one is C1. And then 2C2, x minus a, right? Do you see what I'm doing? Just taking the derivative. Follow that? Okay, what's the next one then? 3C3, x minus a squared, 4C4, x minus a cubed, 5C5, x minus a fourth, and that keeps going. Okay, now let's see what happens at x is equal to a. Left-hand side is f prime of a. What about the right? Everything except the first one disappears because of the x minus a. So that's gone, 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 gone. Right? So C1. Okay, so now we got the second coefficient. That's the first. That's the second. we're going to look for a pattern here. There's no way you want to do it this way to get all of them. But we're trying to find out a pattern. As we do a few more of these, hopefully a pattern emerges, and we can make a conclusion about at n. Now just Cn, any n we want. So let's take a couple more derivatives. F double prime of x. Now the constant goes away. We have 2c2 plus 3 times 2c3 x minus a. And I'm going to write this out this way on purpose, and you'll see in a little bit why. And then here is 5, 4, c5 x minus a third plus a bunch of dots. Okay, now we go to x equal to a again. Left-hand side is f double prime of a, of course. Right-hand side, oh, this shouldn't be here, right? Sorry about that. That's the first power, so that goes away when you differentiate. Right-hand side, gone, gone, gone. All goes away, except the first one, 2c2. Okay, now you get the idea here. Again, we're looking for a pattern, so we'll do this just 2 more times. First one, that one's going to disappear. Right, so that tells us what C2 should be equal to. And F triple prime at A, everything goes away except the first one. 3, 2, C, 3. Okay, now we're going to stop there because the pattern is starting to emerge now. Let's go back and analyze what we saw. I'm going to write this one as 2 times 1. Well, actually, yeah, that's fine. 2 times 1, C2. This is 3 times 2 times 1, C3. And this is 1 times C1. All right, so now what kind of pattern do you notice? Yeah, looks awfully like a factorial, does it? Right, doesn't it? That's 1 factorial, 2 factorial, 3 factorial, right? That's a 2 factorial C2, 3 factorial C3. Generalize that. What would the nth derivative of f at a be equal to? Based on the pattern we just noticed. N factorial Cn. See that? So, therefore, to find the coefficients of the power series we want, The nth one is simply the nth derivative at a divided by n factorial. And this series that we found this way this is called a Taylor series. It's named after this English mathematician, Brooke Taylor, who lived from 1685 to 1731. Okay, a little bit of history. I want to tell you who this Taylor guy is. Well, you can look up more about him, but that's him. Okay, so Taylor series, what does it look like? Any function you want to expand that in this form, power series, you just use Cn is equal to f nth derivative a n factorial. By the way, what's 0 factorial? Yeah, it's defined to be 1. Okay? So when n is equal to 0, the 0 factorial normally looks like that could be trouble. But we define 0 factorial to be 1. So this holds for any n. And if you write out a few terms, we'll see this looks kind of like when n is 0, right? When n is 1, we get first derivative at a over 1 factorial x minus a to the first power, and then the pattern is actually pretty easy to remember. Okay? Okay, so that's the Taylor series. This is actually, as you get deeper into engineering or any kind of science studies, Taylor series shows up in a lot of different places. It's a very, very practical tool for many different applications. And in practice, of course, in applications, we can't deal with infinitely many terms. So typically, we truncate it after n terms. And you call that the nth order Taylor polynomial. And often you see capital T for Taylor and a subscript n for the order. Oops. Sorry about that. So for example, let's go to the third one here. According to the formula we just had, actually, let me change this. What would C0 be in terms of f? Just f of a, right? It's the zeroth derivative, it's a function itself. So C0 would be f zeroth derivative, which is the function itself, f at a, over 0 factorial, that's a 1. So let's write out the third one here. This is f at A plus f prime at A over 1 factorial x minus A plus and I want to go up to 3 and that's it. We just stop it. We chop it off after 3. Now, obviously, this is not going to be exactly the same as the function we're trying to build upon, but for many applications, it'll be good enough. And in general, the nth degree polynomial is equal to the true function minus some remainder Okay, so the remainder for this guy I wrote here would be the fourth one and beyond. These are little things that remain that we ignore. And for Taylor series, you can show that the limit as n goes to infinity, eventually the remainder goes away. That's what it's saying. The more you include, the better the approximation, but eventually it would disappear to 0. The proof of this is pretty complicated. Look in the book. The book took a couple pages to explain, so it's a little bit involved. I don't want to go over that in class, but please do look in the book if you want to see why this is true. Now, today we're going to work on finding Taylor series and see what they look like. Oh, by the way, almost forgot. If A is equal to 0 specifically, then the series is called the Maclaurin series. All right, it's named after this guy, Colin Maclaurin. He came a few years after Taylor. Irish guy. So one's English, one's Irish. So here's what the Maclaurin series looks like. It's the same as Taylor, except all the A's are 0. That's a 1, sorry. Okay, exactly the same as Taylor. It's a special case of the Taylor series when A is exactly equal to 1. A is 0, right? So if you know one of them, you know the other. All right, so let's find the Taylor series for a few functions. Let's start with the Maclaurin series. It's slightly simpler. So here's the function, cosine of pi x over 3. Now, for whatever reason, I want to write this out in the form of an infinite series, specifically the Maclaurin series. you look at the formula here, we're going to need a bunch of derivatives, right? So what we need here, we need f at 0, f prime at 0, f double prime at 0, and so on. We need a bunch of derivatives. And just like before, we'll find out the first 2 or 3 of them and look for a pattern, then generalize that for any n. Okay, so let's keep things organized here. Here's my function. The first derivative is negative pi over 3 sine of pi x over 3. Right? Second derivative, negative pi x over 3, the quantity squared, cosine pi x over 3. Triple prime, positive pi x over 3, whole thing cubed, sine pi x over 3. And let's do one more just for insurance, so we get to see more of the pattern. All right? So here are the derivatives of the function up to the fourth one. We want to know what they are at 0. So let's plug in a 0, and I'll put them on the right side here. I get a 1 for the first one. And f prime of 0, I get nothing. F double prime at 0, I get negative pi over 3 squared. F triple prime at 0, I get nothing. Then quadruple prime at 0, I get pi over 3 to the 4th power. Okay, so what kind of pattern are you seeing here? Here, let's do this way. Let's write this first one as pi over 3 to the 0. Now tell me the patterns that you have noticed. There's quite a bit of them here. Yeah, and which ones are specifically 0? The odd ones. Good. So notice we see that when n is odd, f n prime at 0 is equal to 0, right? Good. That's a good pattern here. Now what are the even ones doing? Good. Excellent. Yep. When n is even, f n prime of 0 is equal to pi over 3 to the n, and they're alternating signs, right? Okay, so these are some of the good patterns we see. And we'll deal with the complexity in a little bit. So what would the fifth derivative be, even without doing any calculation? 0. 6 1? Good. Negative pi over 3 to the 6. Okay, good. Now we can build a series. All right, so the first one is a 1. And then the next one is pi over 3 squared and remember in the formula here, in addition to the derivatives, we need to divide by n factorial. Okay, so don't forget the n factorial. So this is the second power one. We need to divide by 2 factorial times x squared. All right, does that make sense how I got this? This part is clear, right? We just saw that. And then this is the formula in the Maclaurin series. F to the nth derivative divided by n factorial, and then x to the n. What would the next one be? The next non-zero term. It would be plus, right? And then pi over 3 to what power? Third would give me a 0, so let's not include that. So fourth one. What about this guy here? One over 4 factorial, and then x to the 4th. Good, right? We're just building this series based on that formula, and the even ones turn out to be 0. So we're doing. So this guy here is that f double prime at 0, which is this, divided by 2n x squared, and then the first dot here is this. All right, then let's get one more in here. What's the next one then? Let's see. Plus minus pi over 3 to the 6, 1 over 6 factorial x to the 6 plus dot, dot, dot. Okay, any question how we got this? Is it clear to everyone? Nod your head if yes. Good. Excellent. All right. Now the hard part. Writing sigma notation. This is the hard part. So we're going to build the sigma notation based on what we see here. And as usual, let's start at 0 here. So the first term of that series above here, this is n equal to 0. This is n is equal to 1. In my series, I'm trying to build that summation notation here. N is equal to 2. N is equal to 3. Let's take care of the easy part first. I want the signs to alternate, plus, minus, plus, minus. So how do I do that in my summation? Minus 1 to the n. Do I need to change n to anything else? When n is 0, this is 1, right? When n is 1, this is negative. So this appears to fit a pattern. Right? Okay, now what about this pi over 3 part here? When n is 1, it has a power of 2. When n is 2, it has a power of 4. When n is 3, it's got a power of 6, sorry. So what power should I put here for any arbitrary n? Good, excellent. And this guy, the factorial part? How about 2n factorial? Yep. And then the x part, x to the, it's the same power as pi over 3. So 2n, right? So there we go. There is our Maclaurin series. And the important thing here to note is that this thing, I mean, it looks really strange, but it really is equal to pi, the cosine of pi x over 3. Right? There are different ways to express that same function. We put it in a very nice compact form, but hard to deal with in some situations. Here we get a bunch of polynomials. These are easy to differentiate, easy to integrate, whereas that can potentially be difficult. Again, the convergence question is something that should be addressed. To find the radius of convergence, and we saw how to do that before. I'm just going to mention that, but not actually carry out the steps. You use the ratio test here to figure out the radius of convergence for that specific Taylor series. This will be different for every Taylor series in general. So every time you write out Taylor series, you need to do a separate ratio test. We can't use like last time, we cannot use geometric series to say the same for all of them. Okay, questions on this? Okay, good. Let's do more. Let's try exponential, shall we? Maclaurin series of e to the minus 2x. Once again, here's the formula. We need f prime, f double prime, f triple prime, all of that good stuff. And just like last time, you find out a few of these, and then see a pattern, and then generalize. There's the function itself, first derivative, second derivative, third, exponential is really nice. It doesn't really change. All right, so the pattern is very clear here. It's minus 2 to the nth power, whatever degree derivative you want, times e to the minus 2x. Simple. It's a Maclaurin series, so we want to know what's going on at 0. E to the 0 is 1. F prime of 0, minus 2. F double prime of 0, minus 2 squared. F triple prime of 0, minus 2 cubed. Quadruple prime to the 4th. Very clear pattern here. In general, we can say for sure that the nth derivative is going to give me minus 2 to the n. Which is the same as minus 1 to the n times 2 to the n. Okay? All right, now let's build the series. So first we start with the f at 0, 1. Right? And then the next one is a negative 1. You saw that. 2. And this is the first derivative, so it's 1 factorial times x to the first. Right? So again, this guy here is f prime of 0, 1 factorial x to the first. Then f double prime and that's plus 2 squared, 2 factorial x squared. And then f triple prime of 0, it's a negative, I'll put it here. And then upstairs is 2 cubed. Downstairs is 3 factorial x cubed, and so on. Okay, now let's build this in the summation notation. Once again, we have alternating signs. Let's take care of that first. I want plus, minus, plus, minus. So this is 0, 1, 2, 3. This has the same sign pattern as the last one. So minus 1 to the n will give me the plus, minus, plus, minus. What about the numerator here? How would you express the numerator in general for the nth term down the road? 2 to the n, excellent. 2 to the first, 2 squared, 2 cubed, right? Downstairs, the usual Taylor, Maclaurin thing, n factorial. And then lastly, the powers of x. How would you express that? Yeah, that seems pretty clear. So there you go. This series, as strange as it looks, it's exactly equal to e to the minus 2x. They have the same derivative, all the derivatives at 0. All the derivatives are exactly the same at 0. Once you move away from 0, things will be different for a little bit. But at 0, we can say precisely they will look exactly the same. Okay, let's do one more. This time we'll do a Taylor. Same process. It's just that the A is somewhere else. Taylor series of this thing right here at A is equal to negative 3. And just as a reminder, we still need a bunch of derivatives, but not at 0 anymore. A Taylor can be at any other location. A Maclaurin is specifically at 0, but Taylor is somewhere else. But then the rest of it is exactly the same, right? N factorial, and then instead of x to the n, we have x minus a to the n. So same kind of procedure. We carry out the derivatives. And just like before, I'll go 4 or so. This one's kind of interesting. It kind of stops, right? Starting with the fourth one, we don't get anything anymore. It's a third-degree polynomial to start. So first one reduces degree by 1, reduces by 1, and after that, well, these are going to be all zeros, right? Only up to here is it meaningful. Then let's figure out what these guys are at -3. Plug -3 into here. 66 minus 76. 54, and minus 18, of course, right? 0. And then after that, all zeros again. So one thing I want to note here, this will end up being a finite series. Since f nth derivative of a equal to 0 for n is greater than or equal to 4. We have 1, 2, 3, 4 terms to include only. Okay, so let's build them this way again. 66. And then first derivative over 1 factorial x minus a second derivative over 2 factorial x minus a squared, and then one more, right? 0, 1, 2, no, 3 more. This is plus, I'm okay, right, minus 18, thanks. I kind of lost track of that. 3 factorial x plus 3 cubed, and that's it. It stops after that. There's no dot, dot, dot here. You can write dot, 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 but they're all zeros. So simplify a little bit, it ends up looking like this. And as usual, this thing will turn out to behave just like this series we started with. In fact, if you simplify this expression on the left, it turns into that. Multiply this, put it into Wolfram alpha if you don't believe me. You'll get this thing back. Okay, now one more thing I want to mention about finite series. All finite series have radius of convergence of infinity. Because if you think about it, any number you put in here for x, any real number, we're just adding up 4 finite terms, right? So it's of course going to be a finite number. There's no way you can add up a finite number of stuff with real numbers and get infinity. So these guys all have radius of convergence of infinity. Okay, next time we're going to look at why you want to do this in the first place. What is the advantage of doing that? There is one, believe me. Okay, that's it. Have a good weekend. See you Monday.
This is one